Before we begin, one clarification. The podcast serves a navigational function. It presents the structure of the idea, its place in science, and possible directions of development. The formal apparatus, definitions, theorems, calculations, is always available in the text of the work itself. Using modern artificial intelligence tools, you can adapt this material to any level of understanding, from an initial overview to technical analysis. The podcast does not replace the paper. It helps reveal its meaning. I now pass the word to our guests in the studio.
Usually when we think about the end of a universe or like a star collapsing, we picture it as this inevitable, unstoppable physical force.
It's just gravity winning the ultimate arm wrestling match, basically.
Yeah, exactly. But when you look at it through the lens of pure geometry, I mean, the question isn't just about mass and gravity anymore. It becomes a question about the actual fabric of space itself.
Which is such a wild way to think about reality.
It really is. Can the rules of the universe prevent its own geometry from, crumbling into an infinitely dense singular point? Or is the math just completely rigged to fail?
Well, that's exactly the dilemma that two independent researchers, B. Batnin and A. Preece, tackled in this really fascinating new paper.
Right, the one called Hopf-lifted Ricci-Type flow on S3.
Yes. And their whole mission for this deep dive was to figure out if a sealed three-dimensional universe could somehow save itself from collapsing from the inside out.
And crucially, doing it without mathematicians having to step in, play God, and physically cut out the bad parts.
Yeah, which is, that idea of stepping in to cut out the bad parts is actually how we've handled these mathematical breakdowns for a long time.
Like mathematical surgery, right?
Exactly. When mathematicians like Grigori Perelman looked at how the geometry of space changes over time, they used this thing called Ricci flow.
Which kind of acts like a heat equation trying to smooth out the curvature of the universe.
Right. But they inevitably ran into these catastrophic breakdowns, singularities. You get these areas where the curvature just spirals completely out of control and blows up to absolute infinity.
Right. And Perelman's genius solution involved literally pausing the mathematical flow, excising the infinitely dense, broken region of space, patching the hole up, and restarting the clock.
Yeah, he just cuts out the cancer and sews it back up. But, Batnin and Preece are completely removing that safety net here.
So they're asking, what if you are trapped inside a closed cosmological slice, like a fully sealed universe?
Right. You can't just reach outside reality and do surgery on it. You have to find an internal mechanism, a physical or geometric forcing term, to halt the collapse entirely on its own.
I mean, imagine trying to stop a balloon from pinching in half, but you are literally trapped inside the balloon.
Yeah, that's a great way to put it.
And you can only push back using the air pressure and the rubber's own elasticity. You can't just reach outside with a roll of duct tape.
Exactly. You have to work with what's inside. And what makes this deep dive into their work so compelling is that they didn't just throw a theory at the wall to see what stuck.
They were super rigorous about it.
Unbelievably rigorous. They verified their findings using three completely independent methods. They used symbolic algebra, exact mathematical dictionaries for the curvature, and rigorous computers simulations.
So they really left absolutely no room for doubt.
Not at all.
But, okay, before we try to figure out how to stop this universe from popping, I feel like we need to know how it's actually failing. Like, is it squashing flat, or is it shrinking in every direction at once?
Okay, to map that out, we really have to look at the specific shape of the space they're studying.
The Burger family, right?
Yeah, they focus on a highly symmetrical structure known as the Burger family of S3 metrics. Now, without getting lost in the dense topology here, you can basically visualize this space as having two distinct geometric components that govern its overall shape.
Okay, so what's the first one?
First, there's the base, which you can think of as the overall spherical volume of the space. And we measure that with the scale they call A.
Right, the base.
But then, woven through that overall volume is this internal, twisted, circular direction. It's kind of like the threads running through a piece of fabric.
Oh, I see.
And this is called the Hopf fiber. It operates on its own scale, which they call Sana.
And the relationship between that overall volume and those internal threads is basically everything here, right? They measure it with this thing called a fiber squeeze ratio, which they call U.
Exactly. Now, our intuition usually tells us that if any part of a universe collapses down to zero, the whole thing breaks and you get a singularity.
Right, zero volume sounds like a really bad time.
It does. But the math actually shows a massive fundamental difference between those two components. If the internal threads, if that C's value just squashes down to zero, the space actually survives.
Wait, really? It just survives?
Yeah, the curvature of the space stays completely bounded. It hits a ceiling safely at exactly 64 over a to the power of 4.
Wow. Okay, so the space looks degenerate and flattened out, sure, but it doesn't blow up to infinity and break physics?
Precisely. The math essentially treats the Hopf fiber as this kind of soft direction. You can squeeze that internal twist all you want, and the geometric fabric of the space just folds down cleanly onto a lower dimensional surface.
That's wild. So the curvature remains completely manageable.
Yep. The genuine, dangerous singularity, the one that actually destroys the system, only happens during what they call round collapse.
Okay, and that's when the base itself shrinks, right?
Yes. When that overall volume scale, A, shrinks down to 0, when the entire volume vanishes, the curvature mathematically rockets to absolute infinity.
Okay, so think of this space like an empty soda can. If you step on the sides and just flatten it, which is like squashing the metal bends, it looks totally different, but it's fundamentally fine, right?
Right. The structural integrity of the metal itself isn't infinitely stressed.
But if you somehow had a machine that tried to shrink the entire can, like the top, bottom, and sides, all the way down to the size of a single microscopic atom, that's the base collapse.
Exactly.
The pressure inside the metal becomes infinite. The material just fundamentally breaks.
That soda can analogy works perfectly because it isolates that soft direction. And let's take that a step further, because this pinpoints exactly why so many previous attempts to fix this mathematical problem have failed.
Okay.
Under Corollary 1, if we know the fiber direction is soft and its curvature remains safely bounded, any mathematical fix that relies solely on bracing those sides is looking in completely the wrong place.
So if your defense mechanism is only reinforcing the walls of the soda can, it is entirely useless when the entire can is being shrunk to a point.
Exactly. The real enemy here is the volume collapse of the base.
So if we know the real threat is the entire space shrinking to a point, I mean, the natural instinct is to just push back, right? We need to introduce some kind of outward force into the equation to fight the collapse.
You'd think so, yeah.
But when the authors actually tried to mathematically apply standard physical forces to this shrinking space, they hit a massive roadblock. Every single standard approach they threw at it completely failed.
Yeah, Theorem 1 lays this out. They were incredibly methodical about this. They tested forces that only stretched the space without adding volume, what they call traceless forcing.
Right.
They tested forces designed specifically to prop up that internal twisted fiber. But, as we just established with the soda can, those don't address the volume shrinking at all.
So they moved on to something much more powerful, right? A constant conformal term.
Exactly.
But hold on, if the space is collapsing inward, why not just pump it full of whatever drives our actual universe apart?
Which is exactly what they looked at.
Like, when you say a constant conformal term, we are essentially talking about a constant lambda, something behaving like the cosmological constant. Dark energy.
Yes.
We know dark energy pushes the universe apart. So if we introduce a constant push outward, shouldn't that eventually overpower the collapse? Like, why doesn't constant dark energy save the day here?
It seems like the obvious fix.
Yeah.
I mean, it makes perfect intuitive sense. But this is where the pure math of Ricci flow completely divorces from our everyday intuition about pushing and pulling.
How so?
We have to look at the actual rate of growth. The collapse of the curvature in this system isn't just a steady linear march towards 0. As the space shrinks, the geometric reaction driving the collapse accelerates wildly.
It's compounding.
Yes, it grows to the power of 3. It's a cubic reaction.
Wow.
Specifically, at the perfectly round configuration of this space, the rate of collapse is 4 times the square root of 3 times the curvature cubed.
Okay, so it's a runaway freight train. The worse the collapse gets, the drastically faster it accelerates.
Precisely. Now, let's look at your dark energy defense, that constant lambda term. Mathematically, a constant forcing term doesn't scale up aggressively enough.
Because it's just constant.
Right. It only provides a quadratic damping effect.
Mm-hmm.
It pushes back against the curvature to the power of 2.
Ah, so you have a cubic collapse pulling inward, fighting a quadratic defense pushing outward.
Exactly. And it doesn't matter how unbelievably strong you make that constant dark energy term initially. As the space gets microscopically small and the curvature gets astronomically high, a cubic function, a power of 3, will always, inevitably, outrun a quadratic function.
It is a complete mathematical mismatch.
Total mismatch.
A power of 3 will always eventually crush a power of 2. It's like you're trying to stop a tidal wave with a perfectly steady headwind.
Yeah, that's a great visual.
Like, the headwind might feel incredibly strong at first, but the wave's power is scaling up in an entirely different mathematical dimension.
Yep. So standard physics, standard bounded forces, they all fail because the math simply doesn't scale fast enough to catch the runaway train.
Which forces you into a corner. If standard forces don't scale fast enough, what if you just build one that does?
Right.
Like, what if you theoretically design a custom-engineered mathematical force specifically instructed to grow at the exact cubic rate needed to perfectly match and stop the collapse?
And this brings us to what I think is the most thrilling and honestly slightly terrifying part of this deep dive, the mathematical mirage.
Yes, because the authors do exactly that. They engineer a custom term. And on paper, in a simplified model, it looks like a total victory.
It does. They test a curvature-dependent conformal term.
Okay, what does that mean exactly?
Basically, it's a dynamic force that actively monitors the curvature of the space. As the curvature spikes, the force scales itself up at exactly the same cubic rate to perfectly neutralize it.
Okay, so it matches it blow for blow.
Right. In their simplified baseline model, what they call a homogeneous space, where everything is perfectly uniform, smooth, and symmetrical everywhere, this engineered term supplies the exact negative cubic damping required.
So the equations just balance out beautifully.
Perfectly. The collapse halts. The singularity is completely avoided.
But then they take this perfect engineered solution out of the sterile laboratory of the homogeneous model, and they drop it into a real, messy, inhomogeneous space.
Yeah, a space that isn't perfectly uniform.
They use a warped S3 metric, where a neckpinch can form.
Right.
Basically, imagine our balloon again, but instead of shrinking evenly all over, one specific band around the middle of the balloon is pinching inward much faster than the rest of it.
And when they introduce their perfect force into this warped space, a hidden mathematical monster rears its head. Under Proposition 3, they show it's this thing called the Laplacian source.
The Laplacian... Okay, tell me about this, because the discovery of this hidden term feels like a brilliant piece of analytical detective work.
It really is. See, in that perfectly uniform sterile laboratory model, the rate of change of the curvature across the space is exactly 0 because the curvature is identical everywhere.
Right, nothing is changing relative to the rest of the space.
Exactly. But in the inhomogeneous warped space, you have a sharp peak forming right at that pinching neck. The Laplacian is essentially a measure of the curvature of the curvature.
The curvature of the curvature.
Yeah, it measures how much the value at that sharp peak differs from the surrounding wider parts of the balloon. And at a sharp collapsing neck, this Laplacian value is strongly negative.
Oh, man. It's like designing a massive skyscraper in a perfectly symmetrical computer model. The physics engine says the steel beams will hold, the weight is distributed perfectly, it works flawlessly.
Right.
But when you build it in the real, bumpy, unpredictable world, you realize your software simply turned off the wind.
Yes.
The homogeneous math just turned off the Laplacian. Because everything in the sterile model was perfectly even, the equation just completely deleted that variable.
And what makes this so devastating is how the math handles the sign of that hidden wind.
Oh.
Yeah. The core equation governing this flow has a minus sign situated right in front of the Laplacian term.
Wait, so the Laplacian itself is strongly negative at the peak of the pinch?
Minus a negative becomes a positive.
Oh, wow.
This hidden Laplacian source suddenly acts with the exact opposite effect of the intended fix. It actively adds to the curvature growth.
It's helping the collapse.
Exactly. And the authors map this out to show that at the sharpest point of the pinch, this destructive term is just as strong as the protective force they engineered.
It completely cancels out the rescue mission.
Totally cancels that.
They didn't just prove this with equations on a whiteboard, right? They actually ran a Ricci-Type computer simulation to watch it happen dynamically.
Yeah, this isn't just a rough sketch. They used a really sophisticated 200 to 300 point computational grid to track the geometry of the space as time moved forward.
Okay, so what happened in the simulation?
First, they took an unforced space.
Yeah.
And it violently pinched, hitting infinite density and crashing the simulation at a specific time. Tau equals 0.085.
Okay.
Then they injected their perfectly engineered force, hoping it would stabilize the grid. The force fought the good fight. It pushed back against the pinch and held the neck open a little bit longer. But the Laplacian just dragged it down. It still inevitably pinched and collapsed at tau equals 0.119.
So the perfect solution only survived about 40% longer.
Exactly. That simulation is really the nail in the coffin. It perfectly confirmed their analytical prediction.
So the engineered force doesn't actually remove the singularity at all, it merely postpones it.
Right. It acts like a temporary band-aid, relocating the problem slightly down the timeline, but that hidden Laplacian source ensures the collapse is inevitable.
In no converged, accessible regime does this engineered force actually yield a space with bounded, safe curvature.
Correct.
So we can't beat the mathematical collapse with normal forces because they don't scale fast enough.
Right.
And when we engineer custom hyperscaling mathematical forces, they get completely ruined by the messy reality of the Laplacian in uneven space.
Yep.
We're totally out of forces. Like, if we can't push back with a force, we need something entirely different. We don't need a force, we need a wall.
Which is exactly where the authors turn next for Theorem 2. They realize that if you cannot change the differential equation to smoothly halt the collapse, you have to fundamentally change the boundary conditions of reality itself.
Okay, so what do?
They introduce a physical constraint, a literal no-flux reflecting barrier at the absolute minimum scale of the base volume.
They just draw a line in the sand. They basically look at the math and say, okay, the overall volume is shrinking towards zero, and at exactly zero, curvature becomes infinite. What if we just declare that you physically cannot shrink smaller than the fundamental grain of the universe?
Exactly. They set this hard barrier at the Planck length.
But wait, is that even allowed in this kind of pure geometry? Can you just slap a hard stop on reality?
You can, provided you change your framework from pure, abstract, unconstrained geometry to a geometry that is informed by real physical constraints. This is their hypothesis 1.
Okay.
By instituting this Planck-scale barrier, they successfully create what's called a forward invariant region.
Meaning what, exactly?
It means that as the geometric flow progresses over time, once it hits this boundary at the Planck length, the geometry is physically blocked from continuing its descent into zero volume. The inward mathematical drift is simply projected back out.
Wow. And the math actually checks out. Like, the curvature doesn't just build up against the wall like water behind a dam and explode to infinity anyway.
The math checks out beautifully. Because the base volume A is fundamentally prevented from ever dropping below the Planck length, the denominator in their curvature equations can never actually hit zero.
Oh, and if the denominator can't be zero, the total value can't be infinite.
Exactly. The curvature maxes out. In their specific numerical models, they found the curvature is safely capped at roughly 56 times a constant over the Planck length to the 4th power.
So it stays entirely bounded.
Entirely bounded. The singularity is completely avoided, not by wrestling with the forces, but by erecting a geometric stop sign.
This feels like a massive conceptual leap. Like, we spent all this time trying to tweak the engine, and their ultimate solution is essentially just shoving a brick under the tire.
Yeah, but it's not an arbitrary brick. Setting that limit at the Planck scale connects this pure geometry to some deeply profound physics.
Extremely profound. I mean, this isn't just a mathematical trick. It's suggesting a structural correspondence between purely geometric Ricci flow and quantum cosmology.
Specifically, this reflecting boundary mathematically mirrors something called the self-adjoint Wheeler-DeWitt endpoint.
Okay, let's unpack that, because the Wheeler-DeWitt equation is monumental. It's often referred to as the equation of the universe, right?
Right.
It's theoretical physics' attempt to combine the granular probability-based world of quantum mechanics with the smooth, curved space-time of general relativity to basically describe the quantum state of the entire cosmos.
Yes, and to make that equation workable, physicists use something called mini-superspace, which essentially strips the complexity of the universe down to its most basic scales.
Okay.
In that quantum framework, you can establish a boundary condition where there is zero probability flux at the Planck scale.
Meaning what, in plain English?
In plain terms, it means the universe has a zero probability of shrinking out of existence past that fundamental quantum grain. It either bounces or reflects.
Wow.
What Batnin and Preece have done is prove that the only way to mathematically halt this geometric Ricci flow collapse, since we've proven we can't do surgery and we can't use forces, is to implement that exact same quantum boundary condition into the pure geometry.
Which proves this really stark dichotomy, right? You either need a coercive force, which they definitively showed is functionally impossible to implement in an uneven space,
Right.
or you must accept a fundamental physical limit to how small space can get.
Which is tied to the Kretschmann bound in their paper. It's a beautiful alignment between the pure abstract math of geometric manifolds and the messy, granular reality of quantum physics.
The math is essentially demanding that space be quantized. It's practically screaming that space must have a physical floor, otherwise the equations just destroy themselves.
It is a sharp, rigorously checkable verdict. And to be clear, the authors aren't out here claiming to have solved dark energy or unified all of physics. They are very precise and restrained about their claims.
Which makes it even more credible.
Absolutely. They have provided a usable formalism, an exact curvature dictionary, and a definitive mathematical proof that internal forces fail while a boundary succeeds.
So, why should you, listening right now, care about this highly technical deep dive into S3 manifolds and differential geometry?
That's the real question.
Right. Beyond just the mind-bending cosmology of it all, there is a massive, highly practical takeaway here about information, learning, and problem solving in absolutely any field. Simplified models will often lie to you.
That is the paramount lesson of the Laplacian source.
Exactly. We all use models to make sense of the world, whether you are analyzing volatile financial markets, predicting supply chain logistics, or even just trying to understand complex human behavior.
We simplify things to make the math work, to make the problem actually digestible.
Right. We assume our space is homogeneous. But just as that homogeneous reduction hid the deadly Laplacian source that destroyed the engineered force in this paper, in your own field, oversimplifying a problem might hide the very thing that will cause your perfectly logical solution to completely fail in the real world.
Yeah, when you remove the friction, the bumps, the unexplainable variations, the inhomogeneities of your data, you aren't just making the problem easier to solve. You might be fundamentally altering the laws of the system you are actually studying.
You have to always test your brilliant solutions against the chaotic messiness of reality, because that's exactly where the hidden variables live.
Always be wary of the hidden wind in your perfect model. You have to actively look for your Laplacian.
It's a sobering reminder that elegant math isn't always true math when it's applied to a decidedly non-elegant reality.
Yeah, and Batten and Priest didn't just accept the elegant homogeneous solution, pat themselves on the back, and hit publish.
Right.
They deliberately pushed their perfect force into a warped, uneven space to see if it would break, and it did.
That kind of rigorous, almost adversarial stress testing is just the gold standard for finding the truth, whether you're mapping the geometry of the universe or making everyday decisions.
Absolutely.
It shifts your entire perspective on how to trust the tools and models you use to analyze the world around you. But before we wrap up this deep dive, I want to leave you with one final, totally mind-bending concept to ponder tonight.
Oh, lay it on.
We talked about how the universe's ultimate final defense against collapsing into an infinitely dense singularity isn't a magical outward force, but a hard, physical, reflecting boundary at the Planck scale.
The no-flux barrier.
Right.
Yeah.
A fundamental quantum grain that space simply cannot shrink past. But think about what that physically implies for a moment. If the actual fabric of reality is in free fall, collapsing inwards with unimaginable momentum, and it violently strikes that unyielding Planck wall, what actually happens to the fabric of reality at that exact moment of impact?
That is the question.
In their model, the math projects the mathematical drift outward. It reflects. But physically, does the universe just stop and hold there, infinitely compressed, frozen but safe from becoming a singularity?
Oh.
Or, if it truly reflects, does it bounce back? Does a collapsing universe hitting the Planck-Barrier immediately trigger the violent outward expansion of a brand new one? Something for you to chew on.
Subscribe to walk this path together with us. I am Orpheus Praxis, wishing you all clarity. Namaste.